last time we talked about the eigenvalues of a few graphs we were able to figure out. We started with the empty graph and then, of course, naturally jumped to the cycle, which took us on a half-hour detour. But, of course, the cycle is just a really special case of circulant graphs, and these show up in a lot of places. And in particular, when you look at graphs which arise from groups. So there's something called Cayley graphs, where you have the elements of your group are your vertices, and then certain actions act on it. So if your group happens to be the group called Zn, the numbers modulo n, then you can talk about generators are adding or subtracting by some number, some subset. And then what you get are circulant graphs. So okay, all right, so we've done these. So I have some things I'd like to do, and we'll see how far I get, because I ramble. So, but that's okay. We have a whole semester. There's no rush at all. All right. So, are there any other graphs that you want to try?
Didn't we talk about paths right at the end of class?
Well, we didn't solve paths, but we can do paths. So, okay, so we can talk about paths. All right. Now, first off, we should all understand what the path looks like. And so I'm going to say P sub n is the following graph. I'm going to draw it visually, where you have, this is the part where there's controversy, n vertices. So that's P sub n. And so you can label the vertices 1 through n, and I is adjacent to I plus 1 for 1 up less than or equal to I less than or equal to n minus 1. But I think the picture is pretty convincing. Now, the path, it's not quite so obvious how to start. So I'm going to take a small detour. And this will build off of things we talked about yesterday. And, all right, so let's recall that when we talk about eigenvalues, we should, of course, mention we mean adjacency matrix. And I know that that's the only one we've defined. You can imagine every time we introduce a matrix, there will be some activities like this, where we're like, okay, now what happened? But, all right, so we're in the adjacency matrix. We talked about the idea of the adjacency operator, which is to say that when we think of a vector, it's just assigning values to the vertices. And when we apply the matrix multiplication by A, that's the adjacency operator, you add the neighbors. So, observation. If and of course this takes a long time to say things, and it's much funner when you can just wave your hands. All right. So if for our graph G, adjacency matrix A, so we're just introducing our pieces here, and let's say our eigenvector X for eigenvalue lambda. Okay, so we have all of this stuff here. At this point, you're probably saying, wow, well, that's an amazing result. No, these are all assumptions. We haven't even said what the conclusion is. Okay, so, but the point here is I have my eigenvector. And I've noticed I wrote X twice. So that's supposed to be a lambda. All right. The conclusion is, then, if we look at, for the vertices, and there can be any number of these, U1 up through UK, which are subsets of our vertices of G, if X sub U1 and X sub U2, all of these happen to be 0. So in other words, I have entries in my eigenvector which are 0. They can't all be 0, because then it's not an eigenvector. But sometimes you have an eigenvector with lots of entries which are 0. All right, so if we have that, I notice I have an if then, followed immediately by another if then. But okay, we're just layering on our assumptions. You probably can predict what the next thing is. Then if you delete those vertices, so G subtract U1 up through UK has eigenvalue, and what's the punchline? Lambda. Yeah. Well, of course, that's the only thing that would make sense. Why is this true?
The adjacency matrix will just be like a sub matrix, a special sub-matrix.
Well, it is true. So if you look at the adjacency matrix for graph delete vertices, then it is, we would call it a principal submatrix where you delete the same number of same rows and same columns. And but submatrices don't have to have the same eigenvalues as the matrices do. There's a fun fact about interlacing, but it's not guaranteed that they have the same eigenvalues.
You can look at it like a block, like take all of the U's and put them first.
Okay.
So your matrix is like a block. Can I come up and draw this?
Sure.
That's very hard.
And I'll give running commentary for all those watching at home. All right. He's approaching the board. He's picked up the chalk.
So
A matrix has been drawn.
we have some eigenvector that's going to be a bunch of zeros here, and then a bunch of other stuff.
All right. The eigenvector has been rearranged, so all the zeros are at the start.
When we multiply this, we're going to get this, and then this will be lambda times question mark.
Sure, sure, sure.
And so when you take this eigenvector and multiply it by this matrix,
Right.
like these are all zeros, so this doesn't matter.
Ooh, a bold statement. The all zeros doesn't matter. In fact, there's two places where it doesn't matter.
This also doesn't matter.
Good.
And then we know that this times question mark equals all zeros,
That's, yes.
because we get zeros in the output. So what that tells us is that these don't matter, and this times the question mark is all zeros. So when we take just this smaller matrix, call this A, like A prime, we know that A prime times question mark equals lambda question mark. And so not only is it the same eigenvalue, but it's the same, like it's a truncation of the same eigenvector.
Right. Yeah, so the key is we can essentially use the same eigenvector. We just, well, I hate to say it doesn't matter here, but yeah. So the key is, we'll call it A prime. So you can also think of this, if you don't like thinking in terms of matrices, what I'm about to say is essentially the same thing. And it's just phrased in terms of like, well, some people don't like doing linear algebra with matrices. And you know, there's a book, I can't remember which one it is, Linear Algebra Done Right. And then there's one called Linear Algebra Done Wrong. And I think one of them is like, doesn't use matrices. The other one says everything's matrices or something. I can't remember, but anyways, if you think about it in terms of just the eigenvectors are assigned values to the vertices. And if you delete things which are zero, then when you think about the adjacency, you don't change the sum of the neighbors. Because before, the things that got deleted weren't adding anything to you. And of course you say, well, what about if I had a zero? Well, if you have a zero and you deleted it, the sum of its neighbors were zero. Which is why you were pointing up into the upper right corner saying, yeah, we don't really care about that. It just works out. And so you're right. Good. Okay, now at this point you're probably thinking, it's a strange observation. What does this have to do with the path? Well, there's a great idea in math, which is to say, reduce to a previous problem. Okay, so where is something that looks like a path? The cycle looks a lot like a path. All right, so I'm going to think of the cycle, and I'm going to draw a really big cycle. And I'm going to regret drawing it so big, but that's all right. Okay, so there's our cycle, and I want this to be the cycle on 2n plus 2 vertices. Now, you'll notice if I have 2n plus 2 vertices that I really have, I can split it into a few pieces. I can split it into sort of a left side and a right side, and then two vertices opposite each other. And here I have my path Pn inside of the cycle. All right. Now, we just need a few more reminders. We know what the eigenvalues look like. And we know what the eigenvectors look like, right? Because we said the eigenvalues are these 2 cosine 2 pi k over n. But the eigenvectors had a very particular form. Namely, they were roots of unity. So you had a 1, then there was an omega, and so forth and so on. By the time we got here, what would we be? Well, this would be omega to the n plus 1. And then we keep going. Okay, so I should have drawn just before here. So there I have omega to the n. And now you'll say, "Ha-ha, Steve, you fool. None of these are 0. Good, that's true. But I also will notice that these eigenvectors are a little bit complex, right? Because omega is a root of unity. So what we can do is now we can say there's another fact, which I think we said out loud. I don't know if we wrote it down. We'll write it down now. Fact, you have a real matrix with a real eigenvalue. Then there is a real eigenvector. That's not very surprising. It doesn't take much to prove this fact. It's a good warm-up exercise for undergraduates. Even for graduates, sometimes it's a good warm-up exercise. The idea is just think about if you have an eigenvector, split into real and imaginary parts. And then you just carry out the multiplication, and you say, well, either the real part is a non-zero or the imaginary part is non-zero, and then that's going to be my eigenvector. Okay, now we're almost there. I know I'm going slowly, but I just want to make sure we all get there. Someone made an observation about this part right here. Well, what's here? Omega to the n plus 1. What can you say about this entry?
It's negative 1.
You can almost say that.
Why almost?
Well, because there's one more twist to it. It could be negative 1, or it could be positive 1. It depends on what's happening with your particular root of unity. So, for example, 1 is a root of unity. And so the vector that assigns 1 everywhere is an eigenvector. And so if you're thinking about this in terms of a circle, think about how your roots of unity are spaced. You take your circle, and then you space them evenly. We're just saying if you go halfway around, then you probably will think, well, wait, if I go halfway around, I'm at negative 1. But omega is not the smallest root of unity. It could be any root of unity. So you might be taking 3 or 4 steps at a time. So you might have wound up back at 1, or you might have ended up at negative 1. Put another way, I was really hoping to fit it all on the page. Okay, why am I doing this to myself? Oh, there's a little corner up here. Hello, little corner. Okay, so we know that omega looks like e to the 2 pi ij over 2n plus 2. So I being the classic square root of negative 1. I know that's not what I is, but okay, we're among friends, so we know what that means. And j just being some number. So when we look at omega to the n plus 1, well, notice here the 2's have already canceled. The n plus 1's will now cancel. And what we're left with is e to the pi I j. Well, of course, you can think of this, putting parentheses here, as e to the pi I raised to the j. So this is negative 1 to the j power. So it's either plus or minus 1, depending upon which root of unity you're looking at. Okay, so, oh, wake up, wake up. So, how do we get to this observation? What do we do? What do we do?
Are you just setting the well, you want to delete everything that's on the path, don't you?
Well, I don't even need to delete everything that's on the path. What do I want to delete? I don't have to delete all. I just have to delete, my claim is if I can delete those two, what will I have left? I'll have paths. And so if I have something that's an eigenvalue, well, it has to be an eigenvalue of the path. So is there a way I can now use this observation to say, hey, I can delete that and I'm still an eigenvalue? Is there anything that we have that if we know our eigenvalues are real numbers, that's nice. We know 0, 1s are real, so it's a real matrix. Wonder if there's something we have available to us.
Not see how that works.
Okay, well, because you don't see how it works because you don't see the proof. You see the conclusion. So we said the proof out loud. So that's why it's like, we're keeping things back. So the proof out loud was to say, break the vector into real and imaginary parts. If one of them is non-zero, then kapla, success. So what we can do is you can say, look, we have a vector. Let's break into real and imaginary parts. But what do you notice about these two entries? They're totally real. So let's take the imaginary parts. Aha. Yes, that is a fantastic question. We are going to talk about that in just a second. So no, that's a wonderful question. You have like, aha. Okay, but now the punchline, you take the imaginary part of the vector. And once you've done that, then you definitely can delete the top and the bottom vertex, and you have a vector. Now the claim is the imaginary part an eigenvector? It has to be non-zero, because you raised the question, well, what if our eigenvector only had real entries? Well, how can you only have real entries? Which roots of unity? Because so the only roots of unity would be 1s and negative 1s. Okay, so this actually comes in. So that says we don't capture every eigenvalue of the cycle on 2n plus 2. But we capture the eigenvalues which don't correspond to the all 1s vector. Do you recognize what that eigenvalue is?
2n plus 2, or no,
2, because the all 1s vector says add your neighbors. And which it's your degree if you're regular. Now the slightly more subtle one, if I put 1 minus 1, 1 minus 1, and it's an even number of vertices, so I won't come up to like, whoops. So if I'm a 1, my neighbors are minus 1s, then my sum of my neighbors is minus 2. If I'm a minus 1, my neighbors are 1s, and my sum of my neighbors is 2, which is minus 2 of what I started at. So that says the eigenvalue negative 2 will not be part of your spectrum. So yes, maybe?
I think so.
Okay. So the punchline is you capture the eigenvalues, not multiplicities, mind you, but the eigenvalues from this bigger cycle, except for the extreme eigenvalues, 2 and minus 2. So the path, we now have the following. Namely, it's 2 cosine. So if I think about what this is, so put a 2 and plus 2 down here where you see an n, and then say, well, I can cancel out a 2. So it's 2 cosine pi k over n plus 1. And we have it for k equals 1 up to n. Now, you might ask the question, this is a fair question to ask, has this exactly captured the spectrum? Now, there's a few things. One, every eigenvalue we've listed here is an eigenvalue of the path, because we showed how you can construct an eigenvector. Namely, look at the bigger cycle, choose the imaginary part, and knock out 2 vertices. So we have eigenvectors for each one of these eigenvalues. Are these eigenvalues distinct? And if you think about what's happening, it's you have your pi over n plus 1 here, and then your pi n over n plus 1 is just short of pi. So you're sort of evenly spacing along the way, your cosine function. So you have your first eigenvalue where k equals 1 is a little short of 2, and then the next one, and so forth and so on. So we have here n eigenvalues. They are distinct. Can I have any others? Like, do any of these, can they be repeated? Or is there something missing off of our list?
We have n.
So, but what's special about that?
You can't have more than n eigenvalues for n by n matrix.
That's right. Once we know the size of our graph, we can't have more eigenvalues than the size of our graph. So, cool. So now we've done the path. Nice. Nice. Okay. Another entry in our list. Okay, so now let's switch, and instead of doing a graph on n vertices, let's look at the eigenvalues of another nice family of graphs, and that is what we call k, m, comma, n. So these are known as the complete bipartite graphs. And what they look like is you have 2 parts. And one part, there's m vertices. The other part is n vertices. M and n do not have to be the same. They can be. They don't have to be. And then, because it's the complete, it's every possible edge in between. All right. Now, there's a couple of ways for us to approach this. There's some eigenvalues which are really easy, and there's different ways for them to be easy. First off, let's imagine, if you will, we were to draw the matrix, the adjacency matrix. So I'll call this subset on the left A and this subset on the right B. And if I did that, I would see something that you could break up into a nice matrix. What's in the upper left corner? Zeros. What's in the upper right? Ones. And so we'll just shorthand that with a J. Lower left, J, and lower right, 0. Okay. Just from this, I claim that we can get almost all our eigenvalues right away. What do we have? What do we have?
Lots of them are going to be 0.
Lots of them are going to be 0 because?
That matrix has rank 2.
Yeah, this is a rank 2 matrix. And so we're going to have a lot of zeros. And, well, it's a symmetric matrix, and because we know the rank, in particular, we are going to have 0 to the, well, there's m plus n vertices, but then we subtract rank. All right. So that's part of it. So we're close. We're close. So there's just 2 more numbers.
The other two end to end.
Well, we'll figure it out. So there's a couple of things that will happen here. So there's some things we can say. Of course, there are many things that we can say. So let's now do it from a slightly different perspective. So instead of thinking about it in terms of what's the matrix look like, let's think about it in terms of how do I look like locally? Can I construct a nice eigenvector? And I claim, I'm going to draw a picture here. I claim that there is a nice eigenvector which is only non-zero on, say, these 2 vertices here. Can you come up with such an eigenvector that's 0 everywhere other than this highlighted piece? So you get a 0, you get a 0, you get a 0. All these vertices get a 0, but of course, can't be all 0. Yeah, plus 1, minus 1. How does it work?
They have all the same neighbors.
Yeah. So what you have, there's this nice picture. You can call these twins. And that is to say, and this is a general statement. So now we're doing abstract graph theory. You can tell it's abstract when I actually just say, here's my graph. It's just a blob. You know, when you draw individual vertices, that's like, okay, now I'm doing examples. Abstract graph theory, blob. All right, so you have 2 vertices, u and v, and what we look at is we look at what are called the neighborhood of u and v. So we didn't define that word before, but let's just define it now. So what's the neighborhood of u? What's the neighborhood of v?
The set of adjacent vertices.
Yeah, it's what you're next to. You should think of, the nice thing about graph theory is they chose words that make sense. It's a lovely way that way. So twins, they have the same neighborhood. That's what makes a twin. And I guess I should write this down since not everybody always watches the video. All right, have same neighborhood, set of adjacent vertices. And if that's the case, then what you can do is you can assign the value of 1 to one of the vertices and minus 1 to the other, and then you just check that, lo and behold, you go through a few cases. This will be an eigenvalue 0. If you're in the neighborhood, well, of course, 1 plus minus 1 is 0. You should be 0 down here. If you're outside the neighborhood, then all your neighbors have value 0. Okay, so you add to 0. If you're v, everything that you're adjacent to is 0, and it's similar for you. All right. Now, there is another variation, and since we're here, we might as well mention it. What if here the twins are separated? What if, for lack of a better word, we have conjoined twins? U is adjacent to V, but they also have the same neighborhood. So there's sometimes you'll talk about like a closed neighborhood versus an open neighborhood. So a closed neighborhood is the set of adjacent vertices together with yourself. So in this case, they have the same closed neighborhood. I claim that this also has a nice eigenvalue. So remember twins, you got an eigenvalue of 0. So in this case, if the twins are adjacent, put a 1 and minus 1, what's your eigenvalue?
-1.
-1. Because if I'm u, the sum of my neighbors is -1. If I'm v, the sum of my neighbors is 1, which is negative of what I started with. And if I'm anywhere down here, I'm with 0 to start with, and I'm still 0 afterwards. By the way, have we seen an example of a graph with lots of eigenvalues of -1? The complete graph. And the complete graphs have lots of edges between things. So everything is one of these conjoined twins. That's, by the way, not a technical term. Don't start writing papers. Well, suppose you have conjoined twins. Like, what? That's, well, that's true. We can define it first. Okay, so we can make an eigenvector pretty easily. Actually, how many can we make on this side with m vertices? Oh, we can make m choose 2, but then we have to be careful. Well, we have to be a little bit more careful of what? Linear independence. So it's true we can make lots of eigenvectors, especially if our eigenspace is has non-trivial dimension. But we care about linear independence. So the easiest way to make linear independence is just say, okay, I'll fix the 1, and then I'll have a 1, 0, minus 1, and then I'll have a 1, 0, 0, minus 1, just work my way down. And then I can form m minus 1 eigenvectors on the left, n minus 1 eigenvectors on the right. Okay. So, quick observation. This is in particular for this graph, but you'll see that the idea generalizes pretty readily. Suppose I now say I want to look at my last eigenvectors, or the other eigenvector. So for the eigenvectors perpendicular to these ones, if that makes sense. I have a claim. So the claim, I guess you shouldn't put a claim in an observation. So the claim is the eigenvectors are constant on the two parts A and B. So remember, A is the left, B is the right. So the remaining eigenvectors, they have to have the exact same value on the left-hand side for all the vertices. All m vertices have the same value. And all the vertices on the right-hand side all have the same value. And we have mentioned this tool before. What could it be? What could be the tool? If it helps, it has something to do with this perpendicular.
Wouldn't all ones be perpendicular?
That's an example, yes. And that may or may not be an eigenvector, depending upon the situation. Yeah, you take the inner products. So it means something when we say things are perpendicular. And so geometrically it says, oh, if you think about them as being vectors in space, there's or right angle. But in terms of like, well, I can't visualize 25 dimensions. Oh, no problem, just take a dot product. And so if I, just fix one of these vectors. So let's fix this vector. We'll put a little hat on top of it. And now, if I look at, well, here's x1, x2, dot, 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 dot. If I take, and so here's my eigenvector x. Now take x dot v hat. Well, you're going to get a lot of zeros. And the only things you don't get, 0, are where you have that 1 minus 1. So you end up with x1 minus x2. But of course, since these are perpendicular, you get 0, which says that these two entries have to be the same. But now you keep repeating for all of these vectors because you had a whole bunch of them. And you come to the conclusion that everything on that side has to be the same. And then you have the same thing going on the right-hand side. So everything has to be the same on the right-hand side. Now the left-hand side could be a different value from the right-hand side. But it's absolutely the case that on each side they're constant. Yes? Okay, so that makes it really easy for us to find the remaining eigenvectors. Okay, so our last eigenvectors. Okay, so we'll assign a value here for A, and we'll assign a value here for B. We'll say there are m vertices over here, there are n vertices over here, and that these are an eigenvector. Now let's just do our rule about saying, well, what does it mean to be an eigenvector in terms of the adjacency? Well, if I'm this vertex, I add my neighbors. What am I going to get? B times n. Because I have n neighbors, each one has value b. So b times n has to equal the a times lambda. Because it's an eigenvector, it has to be a multiple of what I started with. All right, flip to the other side. Pick a vertex on the the right-hand side. Add its neighbors. What do you get? A times m has to equal b times lambda. All right. Now, in this case, we don't know lambda or a or b. So we have three equations and three unknowns. Sorry, two equations and three unknowns. And you're like, aha, you'll never succeed. Except we say, hey, I don't have to know all the eigenvectors because I can assume I can scale an entry. I claim A is non-zero. Because if A were 0, then all the sums over here would be 0, and I have a 0 vector. Well, that's not an eigenvector. So, okay, let's make A equals 1. Don't lose anything by doing that. So now we have B times n equals lambda, and we have m is equal to b times lambda. Now we have two equations and two unknowns. That's in our wheelhouse. We like that. So for instance, you could multiply, let's see, what could we do? If we multiplied, say, the first equation by b, we get b squared times n. This is not the way I wanted to do it, but oh well. Equals b times lambda equals m. And so you get b squared is m divided by n, or b is plus or minus the square root of m over n. But that's the reason I really should have been solving for lambda, not for b. Okay, but now I know b, so I plug it in. So lambda is n times b, which is plus or minus square root of m over n. And if you clean that up, it becomes plus or minus the square root of m times n. So these are our last two eigenvalues. And we have the eigenvectors are spelled out here. A is 1 and b is plus or minus square root of m over n. All right. So that's cool.
I don't think I understand what that means. Is this like it's an m plus n length vector? And
Which one?
all the entries that go with the A vertices are 1?
Yes.
Okay. And then what the B vertices are?
B.
Okay.
Which is a value. Yeah.
Okay, thank you.
All right. Well, Good. Okay. A couple of observations. This may not have been what you expected, but there is some nice symmetry here. In other words, if I had something that wasn't symmetric in m and n, so if you swap the roles of m and n, it doesn't change the value. And that shouldn't happen, because if you swap the roles of m and n in your complete bipartite graph, it shouldn't change what your complete bipartite graph looks like. So that's a good thing. Another thing you might notice is if you were to look at what these values are on the real line, you'll see you have a bunch at 0. You have one over here at square root of m times n, and you have another one at minus square root of m times n, which is like, aha, this is symmetric across 0. Now, is that a coincidence, or is that a more general pattern?
It's true about symmetric matrices.
Well, not necessarily. If you think about the complete graph for that eigenvalue, it had one way out here, and then it had a whole bunch of them stacked on top of each other. So that one didn't have symmetry around 0 for the complete graph.
Oh, the sum of the eigenvalues is 0 because the sum of eigenvalues is equal to the trace.
Ooh, we're going to definitely talk about that next time.
I don't know if that has anything to do with this.
But it won't, that itself isn't enough to guarantee symmetry. I know, because you probably have learned spectral graph theory things before. So you know, there's low-hanging fruit that everybody learns about when they learn about spectral graph theory. So you guys know that low-hanging fruit, and it's just like you're like, I can almost touch it. I can feel it. Okay, so here's a fun fact. We'll prove half of it now, and we'll prove half of it next time. So G, the graph, is bipartite if and only if the eigenvalues of our adjacency matrix are symmetric around 0. All right, so this is a test. Yes?
Is this symmetry counting multiplicity?
Counting multiplicity, yes, that's a good question. You can cook up things which has symmetry, not with multiplicity, and those are not going to be symmetric. Well, you can cook them up, but you almost always have to cheat a little bit. But which student hasn't cheated? I mean, come on. No, you don't have to tell me. Okay, all right. So, I claim we can do this. We have a few minutes left. We can make a good argument. So, knowing that the eigenvalues are symmetric, implying bipartite is going to be much easier when we have our tool from next time. So that direction is next time. I want to to tell you, it's coming. We're going to do some really fun stuff with the adjacency matrix. So this forward direction is, let's do it now. So you have that your graph is bipartite. All right, that means I have two parts. And I'll call them A and B, and I know that that's really bad form to use A in two different settings, but you know, we have to start recycling at some point. So that's just common usage now. Yes, colors can be helpful. All right, so here's sort of a few observations. If X is an eigenvector, for lambda. Okay, so I have, I'll split my X up into two pieces. So I'll call X A1 up to X AM, X B1 up to X B sub M. Okay, all right. So I have my eigenvector. Then, the following is an eigenvector for minus lambda. Okay.
Are those both M's, or is one of them an M?
Oh, one of them should be, yeah, I'm sorry.
Right, thank you.
We'll switch it to B sub n. All right, I claim that we can now write down an eigenvector for minus lambda.
Want it to be xa1 to xam and negative xb1 negative xbn.
Because that works. That's why you want it to be that way. So you want to flip the signs on one side. The claim is that this is an eigenvector for minus lambda. Well, just think about the adjacency. What's happening? So up here, when you added, you should end up with lambda of what you started with. When you come down here, when you add, well, now it's, because all these were negative, it's negative lambda of what you started with. What about on this side? You should have lambda what you started with. Now here, you got lambda, but there's a minus sign, and so it's minus lambda what you started with. All right, now, what does this mean? It means that for every eigenvector for lambda, there's an eigenvector for minus lambda. That means that the dimension of the eigenspace for lambda is, well, less than or equal to the dimension for the eigenspace for minus lambda. And then you can swap, right? Because then you might say, well, wait a second, maybe you have some extra eigenvectors. But now you get the same thing. You do a dimension argument. So the dimension of your eigenspace for lambda is less than or equal to the dimension of your eigenspace for minus lambda, because you can do this swap. You may have missed something. But now you say, but there's nothing special. Interchange the roles of minus lambda and positive lambda, and you get the same equality. And so you know that the dimensions are less than or equal to one way and the dimensions are less than or equal to the other way. Well, the only way that can happen is that the dimensions must be equal. So this is, again, counting multiplicity, so that we have that now our eigenvalues are symmetric around 0. Okay, so that's the idea. I know I didn't write all that down, but the idea is the important thing. Next time, we'll go the other direction, and I will tell you that the thing we talk about next time is probably the first thing that you ever learn in spectral graph theory. And I know it's like, but wait, it's been like the third week and we haven't mentioned it yet. But it's we're going to learn to count walks. That's the next time.